Hey everyone. In this video, I'm going to go through a couple of common types of model misspecification and their consequences. Okay, the way we're going to talk about this is we're going to look at a simple simulation example. And the goal of this simulation example is to use linear regression to estimate the value of different types of coins and pebbles. So the basic idea is simple. Okay, we have a data set called coins that we will simulate using R. And in this data set, we have we have 100 observations. For each observation, we have a certain number of quarters, dimes, nickels, pennies, and pebbles. Okay. And so we record the number of quarters, dimes, nickels, pennies, and pebbles, and we also record the overall sum that these coins are worth, right? But the problem is we're counting, as we count the overall kind of value of those coins, we make some mistakes. There's a random error in the sum, so it's not perfectly counting all the quarters, dimes, nickels, and so on. Okay, and then what we're going to do is we're going to try to estimate, based on this data set, based on these 100 observations and the kind of sum that is measured with some error, we're going to try to estimate the value of each of those coins, right? So by how much does the overall sum on average increase if we compare two observations where we increase the number of quarters, or two sets of observations where we increase the numbers of quarters by 1, or we increase the number of dimes by 1, right? So basically this will allow us to estimate, if you're not from the United States and coming to the US, and you don't quite know, for a quarter, of course, it's quite obvious, but how much a nickel is worth, you can refer back to this regression to estimate the value of a nickel. Okay, so the basic idea is simple. We have in our table, we simulate all the coins from Poisson distributions, which we talked about in previous weeks. So quarters are drawn from a Poisson distribution, 100 draws from a Poisson distribution with lambda being equal to 5. So in expectation, we have about 5 quarters in each set, in each observation. Dimes are, again, draws from a Poisson distribution with lambda being equal to 10. Nickels, lambda is equal to 20. Pennies is a little bit different. We have the number of pennies is equal to the number of nickels plus some random deviation, which follows a uniform distribution between 0 and 20. So we have between 0 and 20, and this is rounded, so this is always integers. So we have between 0 and 20 more pennies than we have nickels. So that means in expectation we should have about 30 pennies in our data for each observation. And then we also have pebbles. Pebbles obviously are worth nothing, but we have 5 or 100 draws from a Poisson distribution with lambda being equal to 5. So in expectation, around 5 pebbles in our pocket as well. Okay, and as I mentioned, we have an error, and this error is just 100 draws from a standard normal distribution, but we're rounding it, right? So for most observations, this error will just be equal to 0. For some observations, this will be -1 or 1. Few observations, this will be -2 or +2, but nothing really beyond that. There might be, depending on the simulation, maybe we'll observe a 3, but it's quite unlikely with 100 draws, right? So most observations have 0 error. Sometimes we have -1, sometimes +1, sometimes -2, sometimes +2, right? Okay, so how do we then compute the sum? Well, in our data generating process, we of course know the value of each of these coins. So we have 25 cents for each quarter. The sum is increased by 25 cents for each quarter. by 10 cents for each dime, 5 cents for each nickel, and 1 cent for a penny. But we have our error, and this error that I mentioned, that is either -2 or that ranges between -2 and 2, most likely, you can think of as missing a nickel, or counting 1 or 2 nickels too many. Okay, so our deviation is basically miscounting the number of nickels by either -2 or +2. Okay, so the underlying data that we then have is, again, a Tibble, 100 observations, 7 variables. We have the number of quarters in each pocket, so to speak. We have the number of dimes, we have the number of nickels, pennies, and pebbles, as well as the sum. Okay, and of course the sum here, we have $3.44 in our pocket, and we know in that pocket we have 7 pebbles, 29 pennies, 13 nickels, 6 dimes, and 8 quarters. Okay, and now the point is, by running a regression, we can basically estimate the value of each of those coins based on the outcome that we observe, which is the overall value of all the coins that we have in each pocket. Okay, so that's the basic setup. So how can we estimate the value of coins and pebbles in this framework? I'm calling this here model 3A because this is the third part of our this week's set of videos. We of course use stan_glm, and by the way, just to make things simpler and make this computationally a little bit quicker, we're just using the algorithm equal optimizing. So basically we're just looking at the maximum likelihood estimate. We're not sampling from the posterior distribution because we just want to look at the simple point estimates and the standard errors, and this will be much quicker than sampling from the posterior distribution for all the different types of models. Okay, so the first regression model that we will specify is a correctly specified model, in the sense that we include all relevant predictors to predict our outcome, which is again the sum, the total value in each pocket of our 100 observations. We have the number of quarters as one predictor, the number of dimes, the number of nickels, pennies, and that's it for our coins data. Okay, so what is the result if we estimate this model? We of course get point estimates and standard errors for each of those parameters. The intercept of course is around close to 0. It's still within 2 standard deviations of 0, which makes sense, of course, because in expectation, the expected value in our pocket, if we have 0 quarters, 0 dimes, 0 nickels, and 0 pennies, is of course 0, right? So that intercept should be equal to 0, right? For quarters, we have a coefficient of 0.249, which, as I mentioned, if we compare 2 sets of pockets, and those 2 sets of pockets are only differ by the number of quarters, where there's 1 more quarter in one set of pockets than in the other, then in expectation our model predicts that the value of the pocket with the extra quarter is about 25 cents larger, which of course is the value of that particular quarter. Okay, same for dimes, nickels, and pennies. We have 10 cents, 5 cents, and about 1 cent of an increase in the expected value in that pocket if you increase the number of pennies, nickels, and dimes by 1 unit, right? Or if you compare 2 groups that are equal, except for the fact that the number of each respective coin is increased by 1 while the other ones are held constant. Okay. Based on these estimates and standard errors, we can also look at the we can visualize those estimates using Ggplot, and again the code, of course, is included on our Studio Cloud. And we see here the vertical bars are, of course, the true values, in the sense that those are the true actual values of those coin types. And we see, okay, for quarters, dimes, nickels, and pennies, we estimate the true value of each coin based on the simple regression framework, right? A 1 unit increase in each coin count increases the expected sum in each of those pockets according to the actual true value of each of those coins, right? So our model is not misspecified. We're actually identifying all the parameters consistent with the underlying data generating process, okay? So what happens now if we have an omitted variable? If we, for example, drop dimes from our regression equation, okay? Here we run a second regression, M3B, where we again have the sum as the dependent variable. We have quarters, nickels, and pennies. So we didn't include dimes in our regression model, right? If we do this, and if we look at those coefficients, it turns out that the result is still actually, so we still actually get the same, the correct unbiased results for the remaining coefficients. So quarters are still about 25 cents, worth 25 cents. Nickels about 5 cents, at least within 2 standard deviations, and pennies around 1 cent, as we would expect. Okay, so the underlying reason here is that none of these, so the number of dimes is not correlated with any of the other predictors. So whether or not we're including or excluding this predictor, this actually doesn't induce any bias in our remaining estimates. Okay, the only thing that changes, of course, is the intercept, which makes sense, right? Because the intercept now is still the expected sum, the expected value in our pocket. If now quarters, nickels, and pennies, the number of quarters, nickels, and pennies are equal to 0, right? But that doesn't hold the number of dimes at 0. And if you remember, the number of dimes is, of course, it follows a Poisson distribution with mean or lambda 10. So in expectation, there are 10 dimes in each pocket, which implies that in expectation, the value of our sum now is about $1, because it's 10 dimes that are included in expectation. Okay. But the important thing is, again, we can look at this visually. The important thing is that our our estimates for the remaining coefficients are still unbiased, right? Because the number of, as you see here, the number of dimes is just, random draws from a Poisson distribution, is uncorrelated with any of the other number of coins. So even if we exclude this, even if we omit this variable, even though it has, of course, an impact on our outcome measure, we still get unbiased estimates for our remaining independent variables, because we can still say, basically, even though we don't account for the number of dimes across these observations is essentially randomly distributed. So in expectation, it is still true that if we compare two groups and the number of quarters is just increased by 1 in one of those groups, then we can still say that in expectation, the value of that pocket, or the value of the coins in that pocket, is still in expectation 25 cents higher, right? The only difference, of course, is that there's a larger uncertainty, right? So omitting that variable, as we can directly see, increases the uncertainty around our estimates, but it doesn't induce bias. And the reason why it doesn't induce bias is that that variable that we omitted was not correlated with the remaining independent variables, or with the error term for that matter. Okay. Next, we have a second a second model specification where we omitted one variable. Now, instead of dimes, we're omitting nickels. Okay, so now instead we have dimes included in our regression equation, but we removed nickels. So we only have quarters, dimes, and pennies. Okay. It turns out that compared to the previous example, where omitting dimes didn't really bias any of our estimates, now we're actually running into trouble. Okay, we have our quarters that are still worth around 25 cents. We have our dimes that are still worth around 10 cents. But now all of a sudden, pennies are worth around 3 cents rather than 1 cent. Okay, so in other words, we're overestimating the value of pennies. Okay, so why is that the case? If we go back to the underlying data generating process, the number of pennies is correlated with the number of nickels, because the number of pennies is basically just depends on the number of nickels plus some random deviation. So we're just, you know, adding between 0 and 20 pennies to the number of nickels to get our number of pennies, right? So that means pennies and nickels are now inherently correlated. Okay, so that means if we're not accounting for the number of nickels, we're overestimating the number of the kind of effect of one unit of one additional penny, right? Because if we have one additional penny, we also are likely to have additional additional nickels in our pocket. And that means that increasing by not holding the number of nickels constant, we're overestimating the effect of pennies. So this gives you an example of omitting a variable that is both correlated with the outcome and correlated with one of the predictors. If we omit that variable, then we're inducing what is called omitted variable bias, right? So because now the estimated value of pennies doesn't only reflect the pennies themselves, but it also reflects that the nickels, which were correlated with the number of pennies. Okay, so as soon as the omitted variable is correlated with other predictors that are included in the model and is correlated with the outcome, we have to include that predictor. Otherwise, we are likely to induce omitted variable bias, as you can see in this particular example. Okay, so now we kind of covered two different scenarios where we leave out a specific predictor. Of course, we can also have overspecification in the sense that we include variables that are not really necessary in our model. Okay, and this is where the pebbles come in. Of course, the pebbles have no real, like in the underlying data generating process, they don't have any impact on the sum that we have in our pocket, right? So in the fourth model that we're going to look at, we're again including all different types of coins. So we have quarters, dimes, nickels, pennies, but now we're including pebbles. Okay, and as we said, pebbles don't have any value and don't impact the overall sum. Okay. Again, we can look at the results and we see including this meaning or valueless the number of pebbles, which have no direct monetary value, doesn't really impact our estimates, right? So everything is still fine. We're estimating that pebbles, we're correctly estimating that pebbles have a value of very close to 0. Our intercept is again close to 0 as well, and we correctly estimate the value of each of the coin types. Okay, so adding an additional kind of noise factor, an additional variable that is neither correlated with the outcome variable nor with any of the predictors, does not change our estimates significantly. Okay. But now we're going to look at a different example, and here we will slightly modify the number of pebbles that are in each pocket. Specifically, what we're going to do is, rather than just having the number of pebbles that we simulated previously, we're now adding additional pebbles or subtracting some pebbles depending on the error that we simulated earlier, okay? So now we're basically going into our data, and depending on the error that we simulated previously, we remove or add some pebbles to our pebble stack, so to speak. Okay. So what does that mean? What happens if we do that? We're now using, instead of the pebbles, we're now using these correlated pebbles, and we're estimating a fifth model. Okay. And now all of a sudden we have again deviations between like the true data generating process and our estimates. Okay, specifically what we see here is that now all of a sudden while our estimates for our quarters, dimes, nickels, and pennies still looks fine. There's no bias in these estimates, right? Because these are not correlated with the number of pebbles included in our in each pocket. But now all of a sudden, pebbles are estimated to have the same value, at least when we're looking at the point estimates, as pennies. Okay, so if we look at this visually, of course, there's a little bit a larger uncertainty. But despite the fact that pennies, nickels, dimes, and quarters are still correctly estimated, or their value is still correctly estimated, now all of a sudden pebbles are estimated to have a value of a cent, so similar to pennies as well. Why is that the case? Why does overspecification here create an issue? The underlying reason is that now pebbles, this variable that in the underlying data generating process doesn't have any, shouldn't be related to the outcome at all. What it is related to here by adding the error term is that it's now correlated with the error term, right? And so basically by capturing the number of pebbles, we're basically capturing something that is correlated with the error, and that biases our estimates again, right? So as soon as we have parameters, and this is kind of what in kind of econometrics is usually referred to violations of the endogeneity assumption, or exogeneity assumption, I should say, or you have an issue with endogeneity, which is when some of your predictors are correlated with the error term, and then the parameter estimates for those predictors are biased. And so that's one example of those pebbles where we have something that doesn't affect the outcome, but is correlated with the error term and therefore induces bias. Okay. Another example of misspecification, or another issue in your underlying model, can be measurement error. And essentially you can have measurement error on both sides of the equation, right? On the one hand, you can have measurement error on the dependent variable, right? And so in order to kind of evaluate the effect of measurement error on the dependent variable, what I'm doing here is I'm creating an additional sum variable. We're just using our previously computed sum, but we're just adding an additional random error. Here, these are draws from a random normal distribution with a standard deviation of 0.25, so around 25 cents, on average 25 cents additional error in the sum, so quite a substantial increase in the error. And then we're estimating a sixth model using now the new dependent variable with increased measurement error to examine what that impact, whether that has an impact on our estimates, right? And it turns out measurement error on the dependent variable doesn't induce any bias in any our estimates, right? And any all pennies, nickels, dimes, and quarters are still estimated around their true value. The only thing that happens if we have a measurement error in the dependent variable is we have increased uncertainty, right? So as you can see, compare this to the previous model specification, despite the fact that we have the pebbles here, we have much larger standard errors because there's more uncertainty in the outcome, and therefore more uncertainty around our estimated parameters in the linear regression model. Okay, so measurement error in the dependent variable, not such a problem in terms of like bias, but increases uncertainty, as it probably it makes sense that it increases uncertainty to some extent, of course. So what about measurement error on the independent variable? So rather than miscounting, or rather than having additional error in the overall sum that we calculated, now we're introducing measurement error in the sense that we're miscounting the number of quarters, for example, that are included in each pocket, right? So I add a new variable, quarters underscore error, where I basically take the initial number of quarters and I add or subtract between 1 and 2, or between -2 and +2, again, a rounded random normal distribution or standard normal distribution, to the number of quarters, right? So now the number of quarters is between 2 lower and 2 higher compared to the original actual number of quarters, right? So that's inducing measurement error in the independent variable. Now we estimate our next model, and we have our measurement error in the independent variable. So we have quarters that are now measured with error, and we see now that if we do that, and if we look at the coefficient estimates, we now see it's not only the fact that we have increased our error or standard error, as we did in the previous case where we had measurement error on the dependent variable, we actually have biased estimates as well. So since we have measurement error on the independent variable here on the number of quarters that are included in our pocket, we now underestimate the value of quarters. So if we're comparing two groups or two pockets, and increase the number of quarters by 1, then the expected value of that sum is now only about 20 cents higher than without the additional quarter. So we're underestimating the value of quarters. Okay. So this is usually in kind of the econometrics literature referred to as attenuation bias. So measurement error in the independent variable tends to lead to underestimates of the effect sizes. Okay. The last issue that I want to point out, that I mentioned in previous videos as well, is heteroskedasticity. Heteroskedasticity describes the violation of the assumption of constant error variance. And so the way we will introduce heteroskedasticity in our coins and pebbles example is that we first count the number of coins that are in each pocket. So this is just counting just the raw number of coins overall, all quarters, dimes, nickels, and pennies combined. And then we add additional random error around our sum that so we add additional kind of, you can think of additional measurement error around the total sum, the outcome measure that we're looking at. But this error is now not constant for each observation, but it now depends on the number of coins that are in each pocket, right? So you could think of it as an underlying rationale. You could say, like, the more coins I have, the more likely I am to kind of miscount, and the farther I'm off, because, you know, for each additional coin, you can get it more wrong, so to speak. Okay, or, you know, a larger number of coins confuses you or something like that, right? So so in order to take that into account, we add an additional error in our sum, where the standard deviation of that noise is depends on the number of coins, and I just divide this by 1000 to give it like a reasonable scale in the context of the specific simulation example. Okay, so now our dependent variable is the sum in each pocket, but now with the heteroskedastic error, basically. And to give you the long story short, it turns out that heteroskedasticity, or this unequal error variance, again does not bias any of our estimate. The only problem that this creates is that it biases our standard errors. So we have to make sure to take that into account when we want to quantify uncertainty around our estimates, at least from a frequentist perspective. Or we can take into account basically the non-constant error variance in the modeling process itself in order to get more precise estimates. But the point estimates themselves are not affected by heteroskedasticity. Okay, so for us, the lesson to remember is that whenever we have heteroskedasticity, it doesn't bias our estimates, it only messes with our uncertainty, essentially. Okay. So I hope these examples were kind of helpful to kind of wrap your head around some of these issues and consequences of different types of model misspecification, and make sure to go through those code examples on our Studio Cloud and maybe play around with some of those simulation parameters to kind of get a better feeling of what exactly the consequences are of different types of, for example, measurement error and so on. Okay. All right, that's all for that's all I have for you for this week. I'm looking forward to our next Q&A session, and I'll see you next week.